So this kind of leads us into our next kind of turn, our next kind of section, which is bias and variation. So kind of going off of that discussion, we kind of discussed a few of this, but like, I want you guys to think a little bit, like, what is our goal with our prediction model? Like when we say we were trying to make a prediction, how would you describe what's our goal of making that prediction model? Any idea, guys? Yeah.
Be able to describe what will happen when a new event occurs, or to predict with a certain amount of confidence.
Yeah, we want to be able to predict the future, right? We want to predict with stuff that we haven't seen yet, right? That's the whole goal, right? Now, obviously, we don't know what the future is, right? We don't know what future data we will get, but and when I say future data, it could just be your new training, your testing set, right? But how do we measure this goal? Like, what tools have we used so far to like measure saying if we make a good prediction or not?
R-squared.
R-squared, perfect, right? So R-squared is like one that we can really quickly go for a regression model. Basically, hey, if our R-squared is high, then we know we have a good prediction on our data, right? So I kind of showed though a little bit that there are cases when our R-squared value can be high, but we can actually get a too complicated of a model, which actually won't do a good job predicting, right, on future data, which is really our goal, right? So our R-squared kind of like tells us how good our prediction we currently are doing on the current data we have, but it's not quite going to predict for future data. So we have to be really careful about that. And we kind of talked about this model complexity as it relates to all this, is that if we make it more complicated, we can get a higher R-squared, which if we are not careful, that would be our goal, and say, oh, we got an R-squared of 0.999999. But then once we get a new data point, the model is not going to do very well in general as we get more and more new data points that we haven't seen yet. And this is where it's a balance between saying how complex do we make it and how uncomplex, or how simple do we make it? So there's kind of this sweet point that we're going to find, right? So this kind of goes back to like, I wanted to mention about training and testing. So this actually comes from the curriculum again, so you'll see this again. But basically, these data points right here are just some data points. And you can see it's kind of got this like, parabola looking thing. And we say, okay, like when you normally would actually do predictive modeling, you would do training versus testing. So cross-validation, for example, is what we would be using. Is you say, okay, let me separate, like, I think the curriculum has like 70%, usually it's something around like 80-20. So like 80% of my data points will be used just for training, and then 20%, is used for testing, right? Basically saying, okay, let me take the data that I have and let me look at just using 80% of it just to train it, and never use the testing set. And it's picked by random, right? And then we say, okay, cool. I got my model. I got it all figured out. Let's go test that model and see how well it goes against our test set, basically, our data points from the test, right? And we use that to say, okay, how good is our model? And remember, the reason why we're doing this test training versus testing, we're doing that split, is that we want to make sure that we don't train against directly on this data, because then we don't have any way to test it out. We don't have a way to test out, say, well, if there's a new data point that comes out of the population, not our sample, but out of the population, how are we going to be able to predict it? So the idea here is that, well, we'll probably see points that are similar to this if we pull from the population. So let's use that as our testing set, okay? Now, there's a couple ways we can kind of do this, right? You can kind of see there's a few methods that we did a very simple linear regression here, right? That was what the curriculum kind of showed there. And then we can get like a fancy little polynomial going on here. And you can see that fancy polynomial does a pretty good job fitting on those data points, right? But you can kind of see right here, it definitely does better than linear regression, right? But you can see like, oh, it's kind of missing some of those points. And this point's actually really far off, right? Compared to how well it was over here. Like if we measured the R-squared values for here, this would be pretty close to 1. And this one would probably be, like not the best. Like if I had to take a guess, it's like probably like at best 0.8. Like it's doing some of them decently, like these 3 in particular, and this one right here. But this one, and then even these 2 right here are really far off. So these are things that you're like, oh, you know what? Like we didn't have that. We might not have had a great model. And we have to figure out, how do we make it more complicated or more simple, okay? And this leads us into the concepts of variance and bias, okay? And so this is actually an equation comes from that the curriculum points out. It points out to a derivation from Wikipedia, which does a good job actually explaining like the whole thing. So if you're interested in looking at the actual math and understanding where these values come from, that's actually a good way to like practice. In fact, I might have mentioned this before, but if you're looking at mathematical equations, a lot of times Wikipedia is a pretty good resource to at least get you started on it. You always have to be careful with Wikipedia because obviously Wikipedia vandalism and people just, saying the wrong thing or whatever. But for the most part, mathematical equations tend to do pretty well just because people don't tend to change them up. That doesn't mean there's not exceptions to those rules, but it's a good place to kind of resource. And you can always look at the resource that Wikipedia points to, which can also be just as good, if not better. Okay, but basically this is the mean square error, right? And it's built on something called the bias squared. And notice that we're saying the bias of the prediction. That's that y hat is saying that's the predictive model. Saying what's the bias of the predictive model? What's the variance? That's what var is. Variance of the predictive model. And then actually this part right here is basically, this is the extra error that we can't reduce. So this is the variation of the sample itself. So like you can imagine like right here, maybe there is a perfect model that it should follow through, but because of random noise and just randomness, you just have a natural variance, right? And that's what this sigma squared is that variance of that sample. Basically it's noise or I should say error that we can't reduce any further, but we can reduce variance and bias. But what we'll find out is that if you decrease the bias, right, which you get very small errors, you by nature are also increasing the variance and vice versa. So it turns out it's going to be a balancing act trying to figure out what's the best what's the best bias and variance to go through. So this kind of leads into like, okay, cool. What's bias and variance anyway? Like, what do we mean by that? So our bias basically saying like how far off you are from this bullseye. So you can imagine like a target. And I actually think the curriculum shows like a picture of this, which is pretty good, of like high variance, low variance, high bias, low bias. But you can imagine if you had a target, like, a dart board or something like that. Okay. And this is like our bullseye, like right here. Okay. And, we take our, what's it called? We take our points, right? And we say, okay, we're going to just throw our model right at this target. If we were doing a random, it'd just be all over the place, right? But in our model, we'd probably have some clustering of some sort. Our bias means that it's like we have, are getting it really close together. Like we're getting a whole bunch of them right here. But what's happening is that they're way off the target or off the bullseye. Okay. So we can see it's way off to the side. Variance, okay, so this is when you're way off the bullseye. Variance, however, variance is when you have big changes for each throw. So in this case, you might actually be really good at aiming at the bullseye, and you might like get it right here, but then get it right here, and right here, right here, right here, right here. So like you're pretty close. Like you're not off, like this one's like way off, right? Off to the side, but it's all very clustered together. This one, you're very close to the actual bullseye, but you're just having a large variance. You're varying a whole lot, right? So there's these big changes for each time. So I want to kind of think about is like, when would these things occur? Like when would you have this bias way off to the side? Kind of based on what we're learning. When would you expect our model to be way off, even though it's like very, very close? There's not very much variance. You got an idea when we might have this bias? Yeah, maybe kind of tough at this point. So let's talk about something else. So let's see. This actually leads us to underfitting and overfitting. So we kind of showed a little bit of this. And just by the nature of the word overfitting versus underfitting, I'll tell you one of these is overfitting, one of them is underfitting. Which is which? So which one's underfitting?
The linear one.
I'm sorry, which one?
Linear.
The linear one? Yeah. So this one right on top right here, it would be, what did I say? I forgot what I asked. Was it underfitting? Yeah, this is underfitting. Obviously, it's not fitting very well, right? And you can see here is that this would be something closer to high variance, right? It varies significantly off here, right? So it's not doing a good job here. So we usually associate underfitting with our high variance and stuff like that. Now, if we have overfitting, okay, overfitting, it might get super accurate, but it's not quite, sorry, I just want to make sure I was saying the right thing here. not right here, we're actually getting it very, very close on there. So we can actually do this as actually an example of overfitting. So now we can actually talk about like what these errors represent, right? So you can kind of think of complexity. As we get higher and higher complexity, that basically means we're getting closer to overfitting. Like we're overfitting it, right? So you can think of this part, oops. You can think of this part when on this graph, and you guys can see this graph okay? Because it's not too dark or anything like that. Okay, oops. We can think of this as thing, you know, let's see here, overfitting, right? Really complicated. Okay, and then over here we have something like it's underfitting. It's not very complicated. Okay, so this is really what we're getting when, what's it called? When we have this underfitting aspect, or we have a model that's underfitting, it needs to be more complex. It needs to be more complex. We end up getting more bias because it doesn't know any better what to do. Okay, versus overfitting right here, we actually end up getting a higher variance in that sense because it's varying off of that model. And let me just make sure I wrote this right underneath here. Yeah, so you can see I have a little comment out here. So when we have a bias, when we have the wrong assumptions, the model didn't catch all the use cases, right? So when we have a bias, yeah, when we have a high bias, I feel like this thing is backwards. Am I wrong? Oh no, okay. I was thinking this graph was wrong for a second. I might have said something wrong before. But you can think underfitting, high bias. Basically, we made the wrong assumptions, right? The model didn't catch all the use cases. So we saw like if we used a line to model something that was supposed to be more like a parabola, it's making it too simple, right? We need a more complicated model. However, the opposite happens when we make it too complicated, when we start doing overfitting, okay? All that little random noise that we saw, and this is actually really good for this picture, all this like maybe slightly random noise off this model right here is getting added up into the training, and basically it's too sensitive. It's seeing all that little noise and say, oh, that's a little noise. Let me go ahead and predict on that noise. But of course we know you can't predict off random if it's actually random. So it should actually ignore that. We actually need to make it more simple. And that's where this leads us to this sweet spot where basically we balance between variance and bias. And we'll talk about this for mod 3 about how we can adjust for both of those parts. Okay. All right. And there's this article here also in the curriculum. This is where the picture came from, but kind of gives an explanation of this trade-off between bias and variance. Okay. Any questions on any of this bias and variance? Cool. Thumbs up, thumbs down? Cool. All right. All right, cool, guys. So that leads us to our last part in here, which basically it's kind of related to this, but it's kind of a sidestep right now. But and we'll see how they relate later on. But as this regularization techniques, okay. And so one thing that we had before is that with our linear regression, we can use basically our cost function, which is essentially like the squared, right? The R squared is essentially like our cost function. And so we can see here it's our yi minus y hat, which is basically saying what's the data point yi versus the predicted of that data point. I would have actually put, I think, yi underneath here because it's the predictive of that specific I. Like you can think of like taking that specific x and seeing what this y hat do. And that's our cost function here. So you can see like, and this is from the curriculum too, is that you can see this is our data point and this is our model right here, mx plus b. Note that it's a summation, like I said before. The summation just means that there's multiple, what's it called? There's multiple multiple features, right? There's not just one feature, there's many features. There's k number of features, okay? So just know that's where that's coming from, right? So this is a great thing we can do, but one problem we have, we saw with the R squared value, is that the R squared value will keep going up as we make it more and more complicated, right? But the problem is like, well, we don't want it super complicated. We realize that more complication is bad. Clearly our R squared value is pretty good at detecting when it's a underfitting, but it's not so good to figure out when this happens. It's not penalizing essentially what's going on here, right? So we want to basically penalize saying if you have a lot of complication, we want to go ahead and basically make that that quote unquote R squared value lower. And that's really what we call our cost function, basically saying, what does it cost for us to do this calculation? Like the cost of your model, like how well is it doing? So this leads us into a couple things called ridge regression and lasso regression. I usually see it as L2 norm regularization and L1 norm regularization. That's usually in the literature. Sometimes I'll see lasso, but like I think usually people say L1 or L2. Okay, and just kind of know that that's the vernacular, that's the vocabulary, right? So basically the main thing is that we define this hyperparameter, and this hyperparameter is basically something beyond the actual model. It's something that we decide, essentially. We have to decide how big to make this lambda, okay? And basically it penalizes very large, like extra terms, okay? So for large M. So if you imagine right here, if we have many of these values, and if we don't count those values, we just set it to 0, right? And that means we get rid of that feature. And then of course, if you have a small value, it means it has a very small effect. But we want to get rid of the very many large values of M. So what we can do is do the same exact thing before, but in this case, we add an extra lambda term right here. And notice that it's lambda times M squared. And so that would be for each M, like each factor. So if you remember my thing, I put like W1, W2, W3. It would basically be lambda times W1 plus lambda times W2 plus lambda times W3. And basically if those W1, W2s and 3s are bigger, it will actually add to saying, oh, it's not as good. It's not a good, this is not a good model. Now it balances out, thankfully, because sometimes you do need a large value for M or W1 or whatever you call it, right? And that's what this part of the equation does. This part of the equation actually says, okay, see how good is this model in the way it is? And then it says, all right, let's add this extra, basically penalizing term saying, okay, you did really good making your model over here, but your values, there's a lot of complication, so we're going to penalize with you. So your cost function, as we do gradient descent over and over again, if you remember gradient descent, we basically find, okay, what we can do is say, all right, let's make essentially what the maths does, it says, hey, let's make this less complicated. Maybe it's not as accurate on here, but we don't get penalized as much. That's the whole point of this lambda term. It's trying to find that balance of not doing a good job predicting the model, but also not making it so complicated where it starts getting penalized a lot. Okay, so there's two different forms. Basically, there's L2 normalization. So if you remember L2, it's that squared factor, and then L1 is absolute value. So these are almost identical, except you do squared versus absolute value. And there's a couple of reasons why you might want to do one over the other. So with L2, you mostly use this for like overfitting, because all the features, let's see, like you want to do this when you want to prevent overfitting. How do I say this? Yeah. Because obviously we're trying to just get rid of overfitting, but we want to include, if we want to include all the features, if there's like 100 features or more than 100 features, it can be computationally expensive, right? It can add up for many, many variables. So this is one thing, is like, well, if you have many, many, many features, maybe like, like 1 million features, right? This would be really computationally expensive because this value always kind of persists. It doesn't tend to go towards 0 because of the squared factor. And so, but it's really good though for correlated values, because I said spread evenly. That's not quite the right term. It should just be split across coefficients. So like if you have like M1, M2, M3 are all correlated in some factor, this right here will penalize it in the way that it won't get rid of any one correlation factor, but it'll kind of reduce, the coefficients. So the coefficients are more on par with each other. So you're not double counting, essentially. So this is useful for that correlation factor, okay? For L1, lasso regression, it does a couple things. So lasso represents actually least absolute shrinkage and selection operator, which is a mouthful, so we call it lasso. But usually I hear L1 is what I'll hear a lot of. But you'll notice that we talk about shrinkage, which is what this is doing. Basically, it's trying to shrink down the values, but also does selection. And selection just means we're saying what factor, what coefficients, what variable should we keep. And because of this absolute value, it actually tends mathematically, it'll tend towards 0. And we'll actually set values of certain coefficients to 0. So what's really nice is that it can actually reduce, basically get you something called a sparse solution. Basically, you don't have many features, which computationally is a lot easier to deal with than if you have many, many features. Also, another thing, because we can set those coefficients to 0 more easily because of the math of the absolute value. It performs estimation, which is what L2 did, but also does selection. So basically it gets rid of variables that are basically, oh, you're not really helping, get rid of it. So for example, in correlation values, if you have like M1, M2, and M3 are highly correlated, it'll tend to basically get rid of one of those, it'll get rid of those correlated factors and just keep one of them. Now, it's not for certain which one they will keep, but it will try to keep just one of them versus trying to, where L2 will tend to spread out the coefficients, basically spread out the effect amongst multiple coefficients, where L1 just kind of says, nope, you're gone, you're gone, you're gone. Again, this is mathematically. It's not like it's not like something you are deciding. It's the mathematical tendencies for what happens. Okay, so that is regularization, L1 and L2. Basically, it's this extra factor that helps us keep our cost function in check, so we don't overcomplicate it. We want to reduce this stuff. There's other regularizations that you can use, but these are really common because of what we just said. We want to get rid of overfitting. So any questions you guys have on this guy or any of it really?